Welcome back, everybody. We are going to start section 4.4, which is going to take us a while. And this is on more factoring, which we know you love, and factoring polynomials. So we're not just factoring quadratics. Now we're factoring things that have third powers and fourth powers and fifth powers and things like that. So we're going to start with a refresher of factoring using greatest common factor. Remember, this is the number one thing that we always check for, no matter what we are doing. When we are factoring, we always start with, can I pull out a greatest common factor? So for our first example, we have a common factor of x. Remember, when we pull out a GCF, it means we are dividing by that value. So we're left with x squared minus 4x minus 5. Now, a reminder that we will have more factoring to do 95% of the time in this section, even if we pull out a greatest common factor. And so I have 1 times negative 5 is negative 5. The factors of negative 5 that add to negative 4 are negative 5 and positive 1. So we do our factoring there, and we get x minus 5 times x plus 1, and bring down our GCF that we pulled out at the very beginning. And there's our factored form. Example B, again, starting with our greatest common factor. I'm going to pull out 3y to the third from both of these. So 3y to the third on the outside. On the inside, that leaves us with y squared minus our y to the third simplifies out, and 48 divided by 3 is 16. But wait, there's more. Y squared minus 16 is a difference of perfect squares. So we are square rooting each of these. Remember, we don't keep the negative underneath our radical. The square root of y squared is y. The square root of 16 is 4. We personally wrote the square root sign, so there's two answers. One's plus, one's minus. And then bring back that 3y to the third that we pulled out in the very beginning. All right, example C. We're missing a plus sign here. I apologize for that. Go ahead and add that plus sign in there. And then our greatest common factor is going to be 5z squared. So we're left with z squared plus 6z plus 9. 1 times 9 is 9. The factors of positive 9 that add to positive 6 are positive 3 and positive 3. When you do your factoring, you end up with z plus 3 times z plus 3. And then again, make sure you bring back that 5z squared that we pulled out in the beginning. Or you can write this as 5z squared and then z plus 3 squared, because we have the two exactly identical parentheses. So either of these is acceptable. You do not have to write both. One or the other is totally fine. The second thing that we're going to talk about this evening is the sum or difference of cubes. This is a new concept. Sum or difference of cubes has only two terms, and both of them are perfect cubes. So what that means is 8 is a perfect cube because 2 to the third power is equal to 8. 1 is a perfect everything because 1 to any power is going to be 1. You will need to use one of these two formulas to factor the sum or difference of cubes. No other factoring method works. Okay, it has to be these two equations. The other thing that you need to know about these two equations is your second term will never be factorable. Solvable, yes. Remember, not factorable is different than not solvable, but that second set will never be factorable. Let's use these. X cubed is a perfect cube because it's to the third power. 125 is 5 cubed. We have two terms, perfect cubed, subtraction. So we are using the difference of cubes formula. Now when we use the difference of cubes formula, we use just the number, the base, not the exponent, as our A and our B. So our A is X and our B is 5. And that's what we're plugging into our difference formula. So we have A minus B times A squared. A times B is X times 5. We do not keep whatever the sign is in the middle. Okay, you have to follow the formula. Ignore the sign, follow the formula. So 5 times X is 5X, and that's an adding sign in the formula. And then B squared, 5 squared, is 25. This is the answer. That is factored form.